Hello everyone, welcome back. So in the last week, we were looking at the behavior of PN junctions, and we understood, the electrostatics and how the current flows in a PN junction and various non-idealities. So today, we would like to introduce a different type of a junction, which is very, very important. The junction is between a metal and a semiconductor. So in the previous case, we have seen, we have taken a P-type semiconductor and N-type semiconductor, and we have understood what happens. Now we would like to replace one of the semiconductors with a metal. And let's say we can look at, let's say, interface between a metal and a P-type semiconductor or an N-type semiconductor. So what happens in that scenario? Okay. So these type of junctions are also known as Schottky junctions. Okay. Schottky junctions. Or you could also call it a Schottky diode. We will see how the diode behavior comes out. So based on our understanding of materials so far, what do we expect when we have an interface between or a junction between a metal and a semiconductor? So we have understood semiconductors in quite a bit of detail, right? So we have the valence band and the conduction band, and then there's a Fermi level, which depends on the doping density, right? What happens in a metal? So this also we talked about. We said that, there also, even in a metal, there are going to be bands, but in case of metals, this EG, right, is very small. This is one of the scenarios when the metal's band gap is very small, or you could also have or overlap of EC and EV. So essentially, the conduction band comes into the valence band, so that effectively you have a large number of electrons in the conduction band, in the outermost band. Okay, that is a characteristic of a metal. So because of presence of large number of electrons, they are very good conductors. This is what we have studied in the introduction, right? So number of electrons, right? So now what happens when we bring these materials together? How can we analyze it? Okay. So to do that, we need to introduce a few more concepts. Okay, so definitions rather. So this is essentially how the bands will look like. Let's say there are two materials which are separate. They are not yet in connection. Okay, they are separate. Okay, so if they are separate, the metal is going to have a Fermi level, which you have already seen this. Okay, and there is a parameter which we call as a work function of a metal. Okay, that determines how much energy is required to take an electron from the metal to outside the metal. Let's say, we can refer to that energy level as a vacuum level. Typically, you show this. This is essentially a vacuum level. This is a reference level. So the electron is essentially free of the atom, right? So it can freely move about. So that's the reference level. So related to that, if you want to take out an electron from the metal into the vacuum level, the energy reference is known as the work function. Okay. So here we are representing work function in terms of voltage, phi m. Basically, it is telling you in terms of volts. Okay. So charge times the volts will be EV, right? So that's what we have. How many EV of energy is required to take out an electron. So various metals have different work functions. They're not uniform. For example, here in the table, you see that work functions are in the range of about 4.26 is the smallest I'm seeing here, and then the largest I'm seeing is 5.65 platinum. Okay, so you could also have a few other elements like magnesium and things which have even smaller work functions. So you're going the metals have a range of work functions, typically in the range of 4 to 5. The important ones are aluminum, which we use routinely in semiconductor industry, and we also use tungsten sometimes, okay, and a few other materials, of course, right? So you see that there are the units here are in volts, okay. So charge times that will give you the energy, right? So this is work function of a material, which is a very important characteristic. And there is nothing much we can do about this. It's something that you get, when you deposit a material, let's say aluminum you're depositing, we get certain work function. It also depends on the deposition conditions and so on. Okay. So for example, if I deposit aluminum in two different chambers, with two different techniques, let's say, then the work function may be slightly different. But these are something that can be determined experimentally as well. Okay? The other variable or other parameter that we want to define is known as electron affinity. So electron affinity essentially, it's defined for a semiconductor here, and the electron affinity is a measure of how much energy is required to capture an electron and convert the semiconductor into a negatively charged ion. And in the bands, you can show electron affinity as basically this, okay? Amount of energy required to capture an electron and create a negatively charged ion. Okay. Whereas work function was amount of energy required to free an electron. So essentially, in semiconductor, electron can be present in a conduction band. So if you can capture a energy electron from the vacuum level into the conduction band, that's enough, right? So that is the electron affinity of this distance here is shown as electron affinity. Okay. Chi is the symbol. Okay, and this is also known for a material. Okay, for example, crystalline silicon will have an electron affinity of 4.01. Okay, and other materials have different numbers. For example, gallium arsenide has 4.07, and let's say 4.1 for germanium and so on, right? So you have these materials. Now we can also define a work function for a semiconductor. Okay, because semiconductor also has a certain Fermi energy, and then you can remove an electron from that to free vacuum level. So this phi s is the work function of, I'll make semiconductor short form as S, okay, SC I'll call it, or CBC, okay, semiconductor. So the work function of a semiconductor phi s is going to be the electron affinity plus the Fermi energy, right? The Fermi energy here is basically EC minus EF, whatever it is. You have to compute that. So if you have different levels of doping, here, let's say this is an N-type semiconductor being shown here. So the distance here is basically EC minus EF and then plus chi. Right? This is an N-type. Okay. So the work function of a semiconductor is not a fixed number, but it would depend on the extent of doping that we have in a semiconductor. Whereas the electron affinity is fixed. Once you have silicon, the electron affinity is always going to be 4.01. Right? It's crystalline silicon, so I think it's much better known. Okay. So now this is when the metal and the semiconductor are far apart. They're independent. Now, if they are brought in contact, what happens? Okay, they are brought in perfect contact. There are no dust or surface scattering and all that. It's a good contact to make. What happens? To understand that, we would like to draw a band diagram. Okay, let's start with what we know already. So let's say we have the Fermi energy of a metal, EF, and we are taking a semiconductor, which is, let's say, an N-type semiconductor. So I'll take EV and EC, and I'll also draw an EF. Here. Now, the question we want to answer is, what happens? Right? You have brought this metal and N-type semiconductor into contact. What happens? Well, the Fermi level is essentially a measure of the energy, right? It's energy level at which the probability of finding an electron is half. So essentially, to that level, you could think of as energy electrons being there, right? T equal to 0. If temperature is higher, it's going to smear out. And that smearing out is given by the Fermi function, right? So essentially, you could think of it like a water level, right? So water in a tank, that analogy we can use. So now what happens is the Fermi energy of the semiconductor is higher. So there are more electrons there. And on the other side, the electron energy is lesser. So what you can have is basically an electron transfer, right? This is possible. Will there be any hole transfer? That's an interesting question, right? Will there be any hole transfer? Well, I mean, there are no holes here. I mean, the majority carriers are electrons. I mean, there are a few holes, but no, you have electrons at a much higher energy. So that is electron transfer is going to be dominant mechanism. Okay? When we talk of current, we'll see what happens to holes. Okay. So will there be any transfer of dopants? Because after all, we're taking, semiconductor, right? You have lots of electrons. And we say that, okay, fine, there is going to be electron transfer. That is the first thing that we'll accept. Electron transfer from semiconductor to the metal, because semiconductor's Fermi level is higher. Will there be dopant transfer? You should be able to answer it by now. No, there's not going to be any dopant transfer, because dopants are essentially the fixed ions. Remember, always, whenever we are doping semiconductor, we are replacing a silicon atom with, let's say, arsenic or a phosphorus, or N-type semiconductor, it's going to be phosphorus or arsenic. If it's a P-type, it will be boron, right? But these are fixed to the lattice. The dopants are fixed to the lattice. They cannot be transferred, right? So we'll always have only electron transfer. Well, is it possible that there is no energy, no transfer of electrons? Is it realistic? It is not, because we have Fermi energy difference. This is not going to happen at all. So there is going to be an electron transfer. Okay, fine. Electron transfer happens from semiconductor to metal. So what? Will it make any difference to the Fermi energy? Well, at equilibrium, we have studied that in a device, the Fermi level has to be uniform. Okay. So to draw the band diagram for a metal semiconductor, Schottky diode, we will take the Fermi level to be uniform, which we have done multiple times already now. Okay. So once we do that, we know that the Fermi level will be uniform, and metal, there are like lots of electrons. It's not really going to be changing much. Okay. What happens to the semiconductor? Well, away from the junction between metal and semiconductor, it is bulk semiconductor. It's not going to be changing its properties. So away from the junction, you need to have the conduction band and valence band, similar to the separated case. But as you approach the junction, what happens? We have taken some electrons from the semiconductor and then transferred them to the metal. Because of that, there are going to be some dopant atoms which become space charge, right? So this is an N-type semiconductor. If you remove an electron, you will be left with a positive charge, right? So you're essentially removing the electrons. So because of that, what happens is the dopant concentration, the electron concentration reduces at the interface, right? How do we represent a reducing electron concentration? The Fermi energy is going to be away from EC. So because of that, you could expect that the Fermi energy moves like this, right? So basically here, the distance is large. So fewer electrons than bulk, right? Because electrons have gone into the metal. That's why the bands are bending upwards, okay? Implies band, further, I mean, you can look at it whichever way, bands bend upwards. I could even say that this is the opposite case. We can argue in whichever, right? It's the same thing. All right. So what's happening to the semiconductor here? Semiconductor is depleted. Okay. Right. We understand what happens to EC. What happens to EV? Okay. Will it bend in this way? Is it possible? It is not, right? Because we know that band gap cannot change. So this cannot be possible. So what should happen to the EC? The EV will be parallel. Okay. So, I mean, this is what it is going to be. So these are going to be in contact, and this is going to be metal, right? So the recipe is the same as what we have been following in the previous cases. So number one, draw the draw equilibrium Fermi level, equilibrium EF, which is uniform, right? Uniform across the device because there's no external bias. Right? When you apply external bias, it's going to be changing. Number two, look at electron transfer. Determine electron transfer and basically check if it is an accumulation or an depletion. Okay, we will see accumulation later on, but right now it is depletion, right? So electron transfer and draw EC appropriately. Then draw EV, maintaining EG. That's it. Once you do this, this is a Fermi. So this is the band diagram of a Schottky junction. Okay. So now, is there any field in the device? Right? Is there any built-in electric field? Okay. So you should now by now answer that it is there definitely because there is a certain gradient in the EC that is indicative of a electric field present in the device, right? Okay. So now let's. Yeah, this is a diagram which is much neater than what I have drawn. So showing the same thing essentially, right? Because you have this bending as the way I have shown here, and this region we are calling as the depletion region. We clearly understand why that happens because the dopant atoms are uncovered in that region. Okay, and we'll also define this height. It's an important parameter which is called as Schottky barrier height. Okay, why is it a barrier? Well, you have electrons in the semiconductor and the field is pointing out in this direction, right? So electrons cannot cross that field. Electrons experience a barrier. Electrons cannot move into the metal. Similarly, metal electrons cannot come into the semiconductor. So there is a barrier for that. And the height of the barrier is given by phi b naught here. Okay. So phi b naught is going to be how much? It is simply going to be the work function of the metal minus the electron affinity of the semiconductor. Okay. By the way, this is ideal. We will mention how this can change a little bit. Okay. It's not a easy parameter. Okay. Right. So what happens? So yeah, we have the Schottky barrier height. Electrons cannot easily travel across the barrier. Right. We want to determine, of course, whenever there's an electric field, there is going to be a depletion. There is going to be a built-in potential. What is a built-in potential? How do we do that? We follow the same recipe that we have employed many times for the PN junctions. The first step is always to draw the space charge. Because once you know the charge, you know Gauss law, then you can determine the electric field. How is the space charge going to look like in this case? Well, we said that electrons are removed from semiconductors, so they should acquire a positive charge. And that is going to be, it's a uniform semiconductor we have assumed. So this is going to be ND, right? And this is going to be, let's say, some Xn. The depletion region has extended a distance of Xn. You could also call it the width of the depletion region. Okay. The crucial difference from a metal semiconductor junction and the regular PN junction is that the balancing charge, okay, this is positive charge here. The balancing charge is going to be occurring at the interface itself, and it's like a delta function, right? This is your balancing negative charge. Okay. At interface, and it's like, it's a delta function essentially. Okay. Represented by delta function. Why is it a delta function? Well, it's a metal. So there cannot be any electric field in the metal, right? Because the charges will rearrange and then they'll neutralize electric field. So whatever electric field is there, that has to be, it has to be whatever number, you will calculate the amount of electric field. And then the moment you get into the metal, it has to be 0. So the difference in the electric field is the surface charge that's going to be present. And that surface charge is effectively this. Okay. So let's say my semiconductor has, okay, let's do the field and then I'll explain this one more time. Okay, so for now, okay, we said that there is a balancing charge, and this charge, positive, negative charge Q, is going to be minus Q ND Xn. Okay. So that's the at basically 0, you could say, Q of 0. All of the charges only at that point. Okay. Once you have this sort of electric field, what happens? Well, sorry, this sort of charge distribution, you're going to have electric field that we can calculate by dE by dx equal to rho, right? Equal to QD by epsilon silicon times, that's it, QD by epsilon silicon. So that implies that we know from our knowledge of PN junctions that electric field is going to be E is equal to QND, sorry, epsilon silicon times, it's going to be a linear function. At x equal to xn, it has to be 0, and x equal to 0, it has to be minus. So at x equal to 0, it has to be minus. So I'll put it as xn minus x. Okay. So at x equal to xn, it's going to go to 0. Okay. The shape of the electric field is so this is the shape of the electric field, right? This is xn, this is 0. So what you see is there's a sudden jump here. E naught, you can say, right? At E at 0, I could refer to as E0 will be minus Q ND by epsilon silicon times xn. Okay. And E less than 0, Ex less than 0 equal to 0 because it's a metal. So that difference is going to be given by the surface charge, or the delta charge, whatever you have at the interface, because of the boundary conditions for E. Okay. All right. So we have electric field. So what? Well, once you have electric field, you can calculate the built-in potential. In this case, built-in potential is going to be simple because always built-in potential is integral of electric field, right? And so we can write it as area under the curve, right? So that is going to be half times, I'll take it, I don't want to write the positive. So Q and D divided, sorry, negative sign I don't want to take. So xn square. Okay. So the built-in potential is going to be quadratic. Okay. Same as PN junction. So that's why, you could also write, that's why we are showing this as a built-in potential here. So there's going to be band bending, and the bending of EC at, 0 and at the bulk is going to be this difference, built-in potential. And built-in potential can be given as VBI is going to be, in this case, it is Schottky barrier height, other side E50. So basically the Schottky barrier height minus, okay, so you see here, EC minus EF. In the figure, the notation, this is being represented as 5B0 minus phi n. Phi n is essentially the distance between the EC and EV. Okay, that's the definition we are using in the figure here. Okay, by the way, this is from the textbook anyway. Okay, you could look up in chapter 9, I think. All right, so you have this built-in potential, and one of the characteristics of built-in potential is that it's quadratically dependent on the x, and we defined xn to be equal to W. Okay, in this case, because the depletion region is only in the semiconductor, not in the metal, right? So xn is equal to W, implies W is equal to square root of 2 epsilon silicon by Q ND times VBI. Okay. So this is going to be a depletion width. All right. This is how the metal semiconductor junction is going to behave. Now, let me see. This is without any applied voltage. What happens when you apply certain voltage? Same story as PN junctions. Okay. Whenever we apply a positive bias, let's say we are applying this sort of a structure. Now we are considering, let's say, well, imagine as a square, and then I will write it. Let's say there's an applied voltage. VA. Okay. So now when VA is positive, what happens? So this is your junction, and let's say this is semiconductor, SC, this is metal. Okay, semiconductor and metal. And you're applying, with respect to the semiconductor, you're applying a positive voltage to the metal. So when VA is positive, Fermi level lowers, right? VA is greater than 0. When VA is less than 0, the Fermi level is going to go up, right? So in a way, you could think of, keep the EF in the bulk of the semiconductor as constant, or you hold it fixed, and then move the EF in the metal. If you're applying positive voltage, the whole band diagrams have to move down, right? So the way you can show that is, let's say I'll take the EF for the case, I'll draw the Fermi level in the semiconductor EF, and then I will pull the metal Fermi level lower by the extent of the applied voltage. Okay. So this is going to be my QV applied. This is going to be EF metal. This is EFS, I could say. Okay. Now we did that. So essentially what we are doing is we are pulling the bands down. So the barrier height is going to reduce. Okay. So instead of the previous case, you will have a barrier which is like this. Okay. You still, okay, yeah, this is it. Now essentially, because we are pulling it down, we are essentially reducing the depletion. Okay. So this is depletion is reduced. Okay. Because we are pulling down the Fermi level of the metal. Another way to think about it is, essentially we are putting positive charge on the metal, so that's going to pull electrons towards the interface, and so the number of electrons increases in the semiconductor, so you have the Fermi, the bands going down. Okay, so this is what happens when you have positive voltage. Okay, this is for VA greater than 0. So essentially the barrier is lowering. Okay, if your VA is less than 0, the reverse happens. So the same story, we draw the EF semiconductor, and then let's take the EF of metal to be somewhere, EF of metal to be higher. So now we are actually this is, in a way, I'm applying upon negative voltage, right? So this is your QVA. Okay. So you're pulling it up, right? So in a way, you are repelling the electrons from the junction. Okay, you are not helping that process of electrons at the junction. So what happens now is you will have the barrier which is stronger. Okay. Depletion is increased now. Okay. Barrier is stronger, or rather built-in potential is stronger, you would say, right? The built-in potential was essentially this distance. This is VBI plus, now in this case VA. We applied a voltage, but it is negative voltage, right? So always this is going to be minus, but now VA is equal to minus, so that's why the whole thing increased. So here, still the same thing. You have the VBI minus VA, but VA is positive, so the barrier reduced. Now if you apply negative voltage, this becomes VBI plus VR in a way. If you want to rotate, if you want to represent VR as VA is minus VR, so that's reverse bias voltage. So the built-in, the barrier is increased now. Okay. So this is how the bands will change. Okay. So I'll stop this video now. In the next video, we will look at how the current flows in a Schottky diode. Right. Thank you.